Hi, in this video I'll show you how to use a parallelogram to choose the right trigonometry for pretty much any forces problem. And by the way, do give it a look, even if you've tried using parallelograms before and decided you didn't like them at all. And this often happens. You might have decided that you prefer to stick with one triangle instead of two. And a single triangle can often be fine, and it is after all how you probably learnt to add and subtract vectors, as though the vectors are journeys, and then what we take to be the sum total of any two of them is just like going, as we say, as the crow flies, which is to say, a straight journey beginning and ending the same. And that's fine if it works for you, and if you never have any trouble deciding how to arrange the triangle. But with forces, that way the single triangle is missing a trick, which is that with a parallelogram you can always imagine the vector arrows as strings literally pulling, and in fact you draw them all as coming out from the same point, the same particle that they're pulling. And then it's totally natural and intuitive to see the middle string as having the same effect as the other two acting together. Imagine this one pulling at the same time this one is pulling. You know the particle will move roughly in this direction, somewhere in between. And then you can feel that the trigonometry is just going to make this more precise. Now you might have noticed a bit of cheek here. For a start, plenty of forces push, not pull. So that's a bit of poetic license. But also for the trigonometry to work as we feel it should, we must be pretending that the lengths of the strings depend somehow on how strongly they are pulling. Otherwise, how is trigonometry going to tell us the resulting direction of movement? And we don't normally make any such assumption. But yes, this is exactly what you do want to pretend. That you can see the strength of a pulling force in the length of the string pulling. And you'll find it's totally reliable, and you can feel sure that you've chosen the right trigonometry this way. Always sketch. It doesn't have to be a great sketch, something freehand or with a set square. Also go here to this drawing machine if it might help you at all for teaching or learning. And do let me know if it does, or if you have any questions or problems. Thanks. And now an example. A particle P is projected down a line of greatest slope. Smooth inclined plane. They're giving us the motion and the distance. So we are beginning with another suvat. What are we told? It is a trapezium this time because they want to know the initial speed, u. We know the final or later speed is 5. We know that it took 1.6 seconds to get there. The acceleration is one of the things we've got to find, the slope of this line. And we do know also the area under the graph, the distance. Now, let's just look directly at the area of the trapezium as equivalent to the area of this rectangle. Again, the area of a trapezium always is the area of a rectangle, which is kind of the mean average of a larger rectangle, that one there, and a smaller rectangle somewhere. In this case, let's indicate that as well. So we've got 3 different rectangles, all with the base on the horizontal axis. Then the area of the trapezium is clearly the area of this rectangle that's this high here. Well, we can see how high that is now, that rectangle, because we know the area of this rectangle is whatever that height is times 1.6, and it turns out to be 6.4. So we can see we're talking about the number 4. 4 times 1.6 is 6.4. 4/16 being 64. But now it's undeniable that the initial speed is 3. And now then we can say that the gradient is a velocity increase of 2 over 1.6, which we can think of as 20 over 16, 5 over 4 maybe. Or 1.25. Okay, for the second part, the inclination of the plane to the vertical. Let's picture the plane. We're not going to need that bit. Take that out of the way as well. It's a smooth plane. It's a very simple situation. You might start with a whole host of characters. You've got no friction here. We haven't got any tension either. And then we're just left with reaction perpendicular to the slope and weight going down vertically. These are the two forces acting on particle P, which we're representing as a box. That'll do though. But of course, the reaction force being perpendicular to the motion, if we're looking at forces running parallel to the slope, the reaction force just isn't part of that equation. You can get rid of that too. So really we're left with a situation that the particle is moving down the slope exactly with a force, a rate of change in momentum, equal to the gravitational force acting on it. And that force is going to be an appropriate component of the vertical weight. So what we can do is line it up to picture the parallel component, the component that's relevant. We can also see how the reaction force is going to be equal to this component of the weight, and that's just not going to bother us looking down the slope, parallel to the slope. Even better, we don't really have to talk in terms of forces. We've got a weight of mg here. We could label this mg, but I'm not going to. I'm just going to label it g, and then we notice that this component of the weight has to be equal to the ma, the force belonging to P, the force with which it's moving. But I'm not even going to put ma, I'm just the A itself, 1.25. So that's how simple the situation is. And then the angle they want, which is this one, the inclination of the plane, that line there, to the vertical. The ratio between these two numbers is going to be the cosine of that angle. So we can straight away say theta equals reverse cos of 1.25 over 9.8, and that's equal to whatever it's equal to, 1.25 over 9.8 inverse cos, 82.672 82.672 or and we're done. Question 3.